Chapter 8 is about capacitance. Now, capacitance is how much a device can store charge for a given amount of voltage. So we're going to start, first of all, talking about our definition, and then talk about ways that we store charge on these devices that we call capacitors. So again, capacitors are devices. They store charge because they have charge stored within them. They also store energy in the form of an electric field. And they come in a variety of different shapes and sizes, capacities, and so on. Now, the capacitance of a capacitor is basically, think about a capacitor like a bucket. How much will this bucket hold for a given amount of voltage applied? You can hold more charge, the more voltage you apply to these, but they reach a limit at some point. The voltage is going to be so great that they're actually going to break down. The insulating materials inside them will not be able to withstand the electric fields, and essentially you will get a large discharge between the positive and negative charges. But again, thinking about these as buckets of charge, it's one analogy we can use. Obviously, the greater the capacitance, okay, and we use the symbol C for capacitance, the more charge we can put onto them. The bucket analogy doesn't completely hold because of this reliance on voltage. But again, definition of capacitance, how much charge? Now, let's be careful here because, in fact, on the capacitor, there's a positive plate and a negative plate. So the net charge on a capacitor is technically zero. But again, we're storing energy here, and we're storing charge on each individual plate, and there's going to be a strong electric field between the two charged plates, pointing from positive to negative. And the amount of charge on each plate, okay, divided by the voltage to get to that charge is measured in a unit called the farad, okay? How many coulombs do we get per volt? Now, a farad is a very, very large unit because a coulomb, in fact, is a very, very large unit of charge, okay? The electron is just 1.6 times 10⁻19 coulombs. So 1 farad is a huge amount of charge stored in there. We don't normally have capacitors that even approach 1 farad. Typically, what we'll see is microfarads, nanofarads, or even picofarads in terms of the range of how much charge is stored. Of course, that's going to be a little bit different when we get to the end and talk about supercapacitors. But everyday ordinary capacitors that we typically come across in electronic devices, they're going to have microfarads, nanofarads, picofarads in terms of the storage. If it's a much larger capacitor, maybe we'll get into millifarads. Now, the best way to model a capacitor is two parallel plates, again, each with some charge, plus Q and negative Q, on the respective plates. The charge is going to be distributed over some area A on these conducting plates, okay? Both plates have the same area, they're symmetrical, therefore, they're going to have the same concentration of charge. They're separated by some distance d. As the distance becomes smaller and smaller, the electric field becomes more and more intense, and we actually are able to store more charge as the plates come closer. The downside is, as the plates get closer to one another, you begin to approach the point at which whatever insulating material you're using in between is going to break down and the capacitor is going to fail. So getting the plates closer together allows you to store more charge. It increases the capacitance, but it also limits how much voltage you can put across it. Now, for a parallel plate capacitor with nothing in between them, I'll talk about dielectric materials later on. The capacitance is equal to the permittivity of free space. This is a very small constant, as we saw with Gauss's law. It's approximately about 8 times 10 to the minus 12, of course, in SI units. Can't remember. Well, if we look at this, it's relating capacitance to area and distance, so we can come up with the dimensionality there. But the capacitance is equal to this permittivity of free space times the area of each plate, how much surface area these plates have, divided by the distance between the plates. So we see right here, again, this is a really, really small number. So you would need a very, very large area, a very, very small distance between the plates to achieve any appreciable capacitance. I'll give you an example here. Let's say that we have a capacitor. This capacitor is 10 centimeters, that's 0.1 meters, by 10 centimeters, 0.1 meters. And when we take that total area, all right, that's pretty appreciable, 10 centimeters by 10 centimeters. We take that total area, we get about 10 to the minus 2 square meters of area, okay? So I'm going to put that in this part of the equation. 0.1 times 0.1 is 10 to the negative 2 meters squared. I'm going to separate them by a very small distance, only 2 millimeters, okay? So these plates are really, really close together, 2 millimeters. So I put that in the denominator here. What we notice here is that the total capacitance of the system is tiny, okay? It's tiny, 4.43 times 10 to the minus 11 coulombs for every volt. So in looking at this, this would be a 44.3 picofarad, pico being 10 to the minus 12 picofarad capacitor here. So again, capacitors store charge, but in terms of how much charge they can store for the amount of voltage, even almost 1 square foot of surface area is not going to allow very, very much capacitance. We'll see how we get around this later on. What we actually do with the capacitors, and the reason why they're cylindrical, is we take a much larger area, we wrap it up in a roll, just like if you want to move a rug, you wrap it up in a roll, and that's why many capacitors are cylindrical shaped, to maximize the area. Now, another important aspect of the parallel plate capacitor, not only do we store charge, the electric field itself is constant. An electric field is a vector. So when we say we have a constant electric field, we are actually saying that the direction is constant and the magnitude is constant. So for instance, in this particular case here, when we're looking at this, we know that the electric field gets larger, in fact, as the distance gets smaller and smaller. So we've got to be careful how large the electric field becomes before it begins to break down the insulation or the air between the two. But in fact, when we look at the electric field is related to the voltage on each plate. So we can say here that the electric field is equal to the voltage difference divided by the distance between the plates, okay? Of course, volts are joules per coulomb, okay? Electric field is newtons per coulomb. Joules is newtons per meter, so if I take meters and divide by meters, that turns the voltage over distance into, again, newtons per meter, okay? So again, why do we like the parallel plate capacitor when we're studying the electric field? Because first of all, it's very easy to calculate the magnitude of the electric field given some voltage. Let's say that this is 12 volts. Let's say that this is a distance of 0.1 meters. Then we would simply have 12 volts divided by 0.1. We'd have 120 newtons per coulomb of electric field between the two. And again, as I said before, it's always pointing the same distance. It's always pointing from positive to negative. So constant in direction, constant in magnitude, very easy to handle electric fields when we're dealing with this. A real parallel plate conductor, plate capacitor, actually does have some edge effects. As we said, the electric field is pretty constant in between the plates near the centers. As we get to the edge, what happens at the edge is the electric field lines begin to wrap around and curl around like this. So our electric field begins to become less constant at the edges. It becomes weaker. It actually is not constant in direction. So we have to take that into account. Here's a real capacitor. This is done sort of ingeniously. We take a dielectric material and put positive and negative charge on each plate. You can see again the electric field is pretty good in between the plates, and then these dielectric particles actually begin to concentrate the field lines and follow the field lines, just like magnetic particles, magnetic particles will do in a magnetic field. But you can see the electric field again is pretty constant in between the two plates. Now, capacitance is important because it allows us to store charge for a given voltage. It allows us to store energy, as we'll talk about later on. But when we get to alternating current, capacitance has another role to play. It actually creates something called impedance. And impedance is really how much we resist the flow of current in an AC circuit. So different wires, different objects will have the ability to store charge, and therefore will affect circuits differently, okay? So we look at the capacitance of a coaxial cable, and let's imagine at some point we have a positive charge in what is known as the core, and then on coaxial cables, the outside is called the shielding. Say that's negatively charged. We essentially have a capacitor here. We have the electric field lines pointing from the positive charge to the negative charge. And if we do Gauss's law, we know that surrounding this whole thing with the cylindrical surface area right here, that the electric field will go by 1 over the radius, okay? Well, if we think back to some of our relationship between voltage and electric field, the electric field lines follow the gradient of the voltage. So you can get this expression here. It's a little bit complicated how we arrive at that. So let's take a look at our coaxial cable. Again, here's Gauss's law right here. We know if we do a cylindrical geometry, the left side of the equation becomes E times A. For a cylinder, the area is 2 pi r times L. And again, as I said, we surround this with some cylindrical Gaussian surface. And when we do this, we are going to now look at the electric field. The electric field within the coaxial cable will now become Q over epsilon 0 times 2 pi r L. Okay, now here's the important part right here. There's basically a 1 over r dependence. So if I do the integral, if I find the voltage by taking the integral of E dot dl, okay, E dot dl, I know this is a little bit more calculus than most people like. Taking that integral is going to give me, integrate, 1 over r with respect to r, that is going to give me a natural log. Okay. Again, all of these except for r is a constant. Again, I'm integrating with respect to the length, the distance along the electric field lines. And as I do that in the radial direction, I get this expression that I showed you before. And again, that's where the natural log comes from in terms of the capacitance. So you can go through each mathematical step here if you like. Here's where I get the natural log. I put in the limits, the inner radius and the outer radius. Okay, that's the difference in voltage. Now, capacitance is the amount of charge divided by the voltage. Okay, notice that your voltage depends on Q. So now I sort of turn this around and define it in terms of C, and that's where I get this final expression. Okay. Again, coaxial cables typically can store charge. Especially at lower frequencies where the charge has time to build, they can have an appreciable amount of capacitance. Okay, parallel wires are also used to transmit alternating current. When we're using coaxial cables, typically we're using coaxial cables for very high frequencies. Parallel wires are typically used for much lower frequencies. But again, we can use the same approach to come up with an expression for the capacitance. I'm not going to do that here. It's not as important. But again, even parallel wires, which are used in basically transmitting most electricity through our house, have some capacitance. Now, here's something that's very interesting, and this shows us why, even though the Van de Graaff generator can produce very, very high voltages, generally, it's not all that dangerous, at least on moderate scales. Once again, we can imagine that, okay, let's say that I have a Van de Graaff generator. Here's some massive Van de Graaff generators, which are used at, can't remember where this is. I always mix this up between Liberty Science Center and the Boston Science Museum. But we can imagine a more moderately sized Van de Graaff generator, which is held at about 500,000 volts. And we plug it into this equation right here, and we try to see how much charge it holds. Once again, charge on the plates would be equal to the capacitance times the voltage. So even at 500,000 volts, okay, which is getting roughly to about 10 to the 6 volts. I know it's half of that figure, but the capacitance of these spheres is very, very small. Again, here's that little epsilon zero, that 6 times 10 to the minus 11. Okay, so even though the voltage can be very, very large, for a sphere, which is radius much smaller than 1 meter, these are bigger than that. You're not going to store very much charge on there at all. You're going to be storing, millicoulombs of charge at the very most, and even that's going to a bit large. But again, once again, in terms of the main thing here is, yes, different objects will have different abilities to store charge based on the voltage that we put across them. But really the most common geometry that we use to store charge is the parallel plate capacitor. And again, as we go through this chapter, we'll see how we can maximize the area by wrapping these two parallel plates, as I said, much up like a rug, and see how they are able to store energy and store charge. Here's one application for a capacitor, and this is a little bit old, so I think everybody takes pictures now with their iPhone, so this is perhaps a little bit outdated. But here we have, looks like a battery, it's not. This is a little capacitor, it's a little cylinder, and if we were to open it up and unroll it, it would be this long sheet of 2 layers of conducting foil and probably 2 layers of insulating paper or other materials. So again, if you open this up, you'd see this long, I guess a better analogy is like a roll of paper towels. Here you've got 4 layers which are rolled up, but it's like a roll of paper towels that if you unroll the entire roll, you've got a huge area of paper towels, but yet we can store quite a bit of them in a fairly small roll. Well, in any case, you don't want to unroll the capacitor. This capacitor can deliver a lot of energy very, very quickly to this xenon lamp, which is used in this older electronic camera. This is an old film camera, actually. And the flash lamp needs a tremendous amount of power, not much energy, but a tremendous amount of power. So one huge advantage of the capacitor is we know that power is equal to energy over time. It can deliver the energy in a very short amount of time, generating a very, very high power. Now, why do we need the capacitor there? Well, the reason why we need the capacitor there is because and the batteries have been removed in this diagram. If we have batteries right here, batteries are good at producing energy, but they don't produce a lot of power. So the way that this works is the slow electrochemical reactions from the batteries will charge up the capacitor. So we transfer energy from the batteries to the capacitor. When the capacitor is completely full, it's ready to take a picture. And in a very short amount of time, in milliseconds, it'll transfer all of its energy, all of its charge to the xenon lamp. The xenon gas will instantly ionize, produces bright white flash. And again, the capacitor allows it to do something that the batteries really don't have enough power to do. It's interesting because the energy is there. The energy is there, but it can't get out of the batteries fast enough. So we've got to transfer them into the capacitor. And that's one of the big roles that capacitors play. They can deliver a tremendous amount of energy in a short amount of time. So by charging a capacitor, we can release a huge amount of power, again, not for very long and not needing a whole lot of energy. Another application of capacitors, believe it or not, as I'm typing on this computer and I'm going forward with these slides, I am pushing down on what's called a little button capacitor. And these button capacitors have this squishy dielectric material in between 2 conducting plates. One plate on top, which is charged, one plate on the bottom, which is charged, each with a fairly small amount of area. So when I push down on a key, what I'm doing is I'm making the distance between the 2 plates smaller and smaller. And if you recall, for a parallel plate, which is what these little button capacitors are, the capacitance is equal to epsilon 0 A over D. So when I depress the key, what I'm in actuality doing is I'm increasing the capacitance of this capacitor, and I'm transferring charge, more charge to these plates. And as the plate charges, the computer notices that current is flowing into that particular key. So whatever key has charge flowing into it, the computer says, aha, he's pressing key B, and therefore it acknowledges that in its programming. Now, when I release that key, this squishy material, okay, the squishy material will then relax and the distance will become greater, the capacitance will drop, and the charge will come off the plates because it can't hold as much. Its capacitance decreases, can't hold the charge, capacitance comes off, or the charge comes off, okay?